All right, today we are diving deep into the world of algebraic topology. This is a field of math that honestly lets us see things that are otherwise completely invisible. We're going to go on a little journey here, starting with some really simple ideas and ending up with some seriously powerful mathematics.
So if you've ever even glanced at topology, I'm sure you've seen it, right? The classic, a donut is the same as a coffee cup thing. And that's a great little hook, but it almost always leaves you with this exact question. Okay, I get the analogy, but where's the math? How do you actually prove that? Well, that is exactly what we are going to unpack.
You see, topologists have this idea they call rubber sheet geometry. Just imagine that every shape is made of this infinitely stretchy, bendy rubber. You can twist it, you can stretch it, you can squish it, but, and this is key, you can't rip it and you can't glue new bits on. In that world, a coffee cup can just be molded into a donut. Why? Because they both share one single essential feature. They've each got one hole.
But, this isn't just some fun little thought experiment. This whole rubber sheep idea is governed by some very precise mathematical rules. So let's lay out the actual rules of the game.
Okay, the official fancy term for one of these transformations is a homeomorphism. Now, I know that definition looks a little scary, but all it's really describing is a perfect, totally reversible transformation. Bijective just means it's a perfect one-to-one mapping. No points get created, no points get destroyed, and the continuous parts, that's what ensures there are no sudden rips or tears, no gluing things together, it's all smooth.
So really, all that formal language just boils down to these three simple rules for our game. 1, you can stretch and bend all you want, but 2 and 3 are what you can't do. You absolutely cannot cut or tear the shape, and you cannot glue different parts of it together. You have to work with what you've got.
And this leads to some really kind of surprising results. So under these rules, a triangle is actually the exact same thing as a circle. Yeah, really. Those sharp corners, the straight edges, they just don't matter topologically. You can smooth them all out. The only thing that matters are the deep, fundamental properties that survive all that stretching and squishing.
Okay, so this brings up a huge question, right? If we can change so much about a shape, if corners and lengths don't matter, how in the world do we tell two shapes apart? The answer is to hunt for the things that don't change. We need to find something called a topological invariant.
And this brings us right to our main challenge. I mean, intuitively, we all know a sphere is different from a donut. One has a hole, one doesn't. But using the rules we just set up, how can we prove, with cold, hard math, that you simply cannot turn a sphere into a donut without breaking those rules?
And the solution, like we said, is to find one of these invariants. It's some property. It could be a number or even a more complex algebraic thing that stays exactly the same no matter how you deform the shape. If two shapes have a different value for this invariant, then bam, they cannot be the same. It's like a mathematical fingerprint.
Now, for our sphere versus donut problem, the most obvious invariant is, of course, the number of holes. A sphere has 0. A donut has 1. And since 0 does not equal 1, they have to be topologically different. Case closed, right? Well, not quite. The real question is, how do we get math to see and count those holes with total risk?
And this is where the algebraic part of algebraic topology finally comes into play. We are going to build a tool, an algebraic X-ray, if you will, that can look deep inside a shape and count its features without us ever having to just look at it.
To get how this works, let's just shift our perspective for a second. Imagine you are a tiny little ant, and you live on the surface of a donut. To you, everywhere you walk, your world looks pretty much flat. You can't see the big picture. How could you ever figure out that your entire universe is built around a giant hole? Well, the secret is all about drawing loops. Let's say you're on a sphere, and you lay down a piece of string in a closed loop. No matter where you draw it, you can always just pull on that string and shrink it all the way down to a single point. That loop is what we call the boundary of the little patch of surface that it encloses. But try that on a donut, and everything changes. If you draw a loop that goes around the central hole, like this red one here, you can't shrink it to a point. It gets stuck. It's snagged on the hole. And the same thing is true for a loop that goes around the tube itself, like this blue one. These loops are fundamentally different. They are not the boundary of any piece of the surface. So right here, this is the whole game. On the left, you've got loops that are shrinkable, they're boundaries. On the right, you have these special, non-shrinkable loops that are not boundaries. And it's these loops on the right, the ones that signal a hole, that our algebraic X-ray is designed to find and to count.
And that really brings us to the big idea. Algebraic topology is this amazing process of attaching algebraic objects, things like numbers or groups, to these geometric shapes. It basically translates a geometry problem we can't easily solve, like how many holes are there, into an algebra problem that we can solve with absolute precision.
The specific tool we use to do all this counting is called homology. You can think of it as the actual machine that runs our X-ray. It takes our shape, it analyzes all the possible loops and cycles, and then it spits out a precise algebraic signature that tells us everything about its holes.
Now this is the engine of the machine, the homology group. And yeah, the definition is a bit technical, but it's doing exactly what we just talked about. It's looking for n-dimensional cycles, for our purposes think loops, that are not the boundaries of something in the next dimension up. It's the formal mathematical way of capturing that idea of a loop getting stuck on a hole.
So, to put it simply, the first homology group, H1, it counts the kind of holes we've been talking about, these one-dimensional tunnels that a loop can get caught on. But then the second homology group, H2, it counts something else, two-dimensional holes, basically hollow voids, like the empty space inside of a basketball.
And here are the results from our X-ray. The signatures are completely unique. A sphere has 0 1D holes, but it has one 2D void inside. A circle has one 1D hole, but no void. And then there's the torus, our donut. It has one 2D void, but look at its H1 group. It tells us there are two fundamentally different types of 1D holes, one going through the center and the other wrapping around the tube. That result for the torus is the big payoff. We didn't just prove it has a hole. We proved it has exactly two independent, non-shrinkable loops. This algebraic signature is its permanent, unchangeable topological fingerprint. And it proves, beyond a shadow of a doubt, that it is fundamentally different from a sphere.
So we've gone all the way from a simple coffee cup to some pretty abstract algebra. What's the big picture here? Why does this whole idea matter so much?
Well, here's what's truly miraculous about it. To actually do these calculations, mathematicians often have to chop a complex shape into a bunch of simple pieces, maybe like a mesh of tiny triangles. But the amazing part is, it doesn't matter how you slice it up. No matter how you do the calculation, the answer you get for the homology is always the same. It is a deep, fundamental truth about the space itself.
You know, we've just been looking at simple shapes we can see in 2 or 3 dimensions. But this algebraic X-ray, it works in any dimension, 4, 5, 100, 1,000. It lets mathematicians probe the structure of high-dimensional data, of abstract spaces that we could never, ever hope to visualize. And it leaves us with this just incredible question. What other unseen structures are out there, in spaces we can't even imagine, just waiting to be discovered by these tools?